I honestly believe that I can save most of the coral species of the world, and with a little help, here is how I can do it. Certainly we should try to save the coral reefs, but we should also be trying to save the corals. Those are two very different goals. Many of the coral reefs are located in areas that will become more and more uninhabitable as water temperatures continue to rise due to global warming. So our focus should be not just saving the coral reefs, but it should also be on saving representatives of all of the coral species. To do this, we need very efficient and inexpensive ways to relocate massive numbers of all types of corals, including hard corals and soft corals. We need to be relocating small populations of all corals to areas that have better water conditions that will allow for their interim or long-term survival. This video will show you how we can do that right now without delay. My company was called Scientific Coral, and I researched coral propagation from 1990 until 2010. What I learned was that we can very efficiently and inexpensively propagate thousands of small polyp stony corals, large polyp stony corals, soft corals, and gorgonians using methods that we developed that nobody else seems to have figured out yet. But why is it important to save all types of corals? Maintaining coral reef biodiversity is absolutely essential. Coral reefs are an extremely complex, synergistic web of all types of organisms. We can't just save a few hardy species of stony corals. We have to save as many types of corals as possible. It's absolutely critical that we propagate soft corals, along with large polyp stony corals and small polyp stony corals, in order to maintain the biodiversity of our coral reefs. A coral reef with only a few species of hardy stony corals is no more a coral reef than a palm oil plantation is a rainforest. Current methods for asexual stony coral propagation use either a two-part epoxy, cyanoacrylate glue, or cable ties to attach the stony coral to the surface of a substrate. Embedding the stony coral frag is far quicker and much stronger, since the fragment is firmly anchored inside the substrate. Using our methods, we can mass produce thousands of all types of corals, as you will see in this video. There are two different cube methods that I will show you today. One for embedding SPS, LPS, and gorgonian corals, and the other for attaching and growing soft corals. Let's talk about our method for producing SPS corals first. Using the embedded method, we can mass produce thousands of SPS stony corals. This is our method for filling our embedded cube plates with stony coral cuttings. Here I am mixing up a batch of non-caustic, coral-safe material that will make up the cubes. It's a very simple process, and using this method we can mass produce thousands of SPS or LPS stony corals. You have to embed the coral frags very quickly, as you will only have a few minutes before it sets up. The key to the success of the embedded cube method was finding an inert, non-toxic substrate material that would not cause any damage to the coral frag when it was inserted, or to the system where the plate is placed after it sets up. For this demonstration, I am only using plastic cuttings. Ordinary concrete cannot be used as it is very caustic to anything living. We researched a lot of different substrates, and through trial and error finally developed one that worked well. None of the more than 120 types of hard corals we embedded experienced a negative reaction to this material. It takes about 20 minutes for the material to set up enough to put it back into the saltwater system. During that time, it's important to prevent the corals from drying out. You can lightly spray them with a handheld mister and keep them covered up until it sets up. Once the plate material sets up very solidly, within a few days, you can just let them grow out longer on the plates, or pop out the individual cubes, or either insert them directly on the reef, move them to individual artificial rocks with keys or combo rocks, or any other options you choose. The cubes are completely interchangeable. They can easily be popped in and out of the egg crate matrix. We leave the four corners open to use them for supporting the trays in the system. We also developed a key method where each rock has a key on the bottom that is inserted into the egg crate for storage, as you can see here. This is very convenient for storage or shipping large numbers of corals. Or a circular hole can be drilled into the reef substrate with a hole diameter matching the diagonal of the cube, and the key can be inserted. It's possible it can be wedged firmly enough into the hole on the reef that no adhesive is required. You can very quickly and efficiently install large numbers of corals this way. Many of the plates with small rocks in this video use this setup. We found that juvenile corals do much better than adult corals when moved to new areas. Here you can see an example of real yellow cup coral cuttings that have just been embedded in the cement matrix. And here's that same plate about 4 months later. Here the cubes with the coral cuttings have been inserted into artificial rocks for grow out. This is about 9 months from when the frags were first embedded. Here you can see a newly embedded plate of green bird's nest, and here is that plate about 1 month later. Here we put the cube into an artificial rock, and at that point they can actually be installed in the ocean. These green bird's nest Seriatopora hystrix are at various stages of grow out. And this was probably about 9 months old since it was first embedded as a frag. Here you can see a recently embedded plate of Acropora nana. We used a checkerboard pattern so as not to crowd them. And here are growouts of that plate. These are ready to pop the cubes out and use whichever way you choose to use them. Here's a recently embedded plate of Pavonicactus. We used every cube on this one. And here is the grow out of that plate. And these are corals grown using the same embedded method. Here the cubes have been inserted into larger artificial rocks for grow out. In some cases you can still see the outline of the cube. All of the SPS stony corals in this video were grown by this method of embedding a coral fragment into a cube of non-caustic liquid cementitious material. Later in this video you will see many more stony corals that we grew using this method. We also use these embedded cubes for asexual gorgonian propagation. We took cuttings of 5 species of Caribbean gorgs and successfully embedded them. Here's an example of a prototype grow-out system. This is our method for getting soft corals to attach to our tonal cube plates. It's very fast and easy once you understand the method. We use the same polystyrene egg crate material for tonal cube plates that we do for stony corals and gorgonians. These aren't real soft coral cuttings. They are actually small mushrooms I cut up. I'm using them for demonstration purposes only. And this is how we fill the tonal cubes. Fast and simple. This plate takes me about 2 minutes to fill up 117 holes. Our goal is attachment of the soft coral to the inner wall of the tunnel. That's the hardest part about propagating soft corals, getting them to attach to a new substrate. Soft corals don't have a solid stony skeleton, so they can't be embedded. They only have sclerites, which are like small stony needles. This plate has 117 holes, and it only takes a few minutes. You can also use a turkey baster for some types of corals. Make sure the cuttings are not too large for the tunnels. You need to leave access for water to pass through. It's also critical that there is no detritus in the system that might clog the screens. After the tunnels are filled, apply another netting on top of it, and then a matching empty egg crate plate on top of the netting. It's important to line up the egg crates so they don't impede the flow of water. But if they are all the same size, it should be easy to match them. Then apply rubber bands on all four sides. The quantity of corals produced is more important than their size. Give them the right conditions, and many of the branching or plating corals grow like little weeds very quickly. So here you have a completed tunnel cube assembly. Now you can place it in a detritus-free system with moderate current and good lighting. Attachment should take from 15 to 60 days depending upon the species. Here you can see a newly filled tunnel cube plate of fluorescent green leathers. The cuttings have attached and already have started to grow out. Here we have installed the cubes into small artificial rocks for further grow out. And these fluorescent green leathers are on rocks that have the key on the bottom to lock into the egg crate. Here is a fluorescent green leather that we divided into 2 stalks. And this one we've divided into 4 stalks. Here's a group of zoanthid cubes that have just been inserted into rocks. And you can see how they quickly grow and cover the rock. And here the cubes of clavulary have been installed, and you can see how they too have completely covered the rocks. The holy grail of coral production isn't survival or coral growth. Those are easily accomplished. The holy grail is attachment, getting the coral cuttings to attach to a new substrate. Yes, the big challenge with asexual coral propagation, meaning propagation by fragmentation of a coral colony, is attachment. Getting the coral fragment to attach to a new substrate where they can then grow out and be moved to their future reef when ready is the key to success. We devised a way to encourage the coral fragment to attach to a new rocky substrate. It was a long process for us to figure out how to do this. The toughest corals to attach were the soft corals. Getting soft corals to attach is like getting jello to attach to a rock. They don't have a stony skeleton, so you have to find a way for them to attach on their own. Getting stony corals and gorgs to attach is much easier. Even so, the current methods for them are incredibly time-consuming, inefficient, and costly. We found a much better way. We use the embedded method for SPS, LPS, and gorgs, or use the tunnel method for soft coral attachment. It's absolutely critical that we propagate soft and LPS corals along with stony corals in order to maintain the biodiversity of our coral reefs. This is a newly poured plate with small frags of Galaxia. This coral is extremely easy to grow in massive quantities. Here is a plate of Galaxia that has the key lock underneath. And here is a tray of Galaxias with flat bottoms. Here are some other large polyp stony corals that we grew using the embedded method. This is a green cup coral that we actually sawed up with a diamond blade on a tile saw. It doesn't damage the tissue much, and we get a nearly 100% success rate of embedding and survival. These are various other LPS corals, including the beautiful red blastomussa. Most are locked onto the plate using our key method. Even when you cut an uneven wedge of tissue, they eventually grow back to a symmetrical shape. It's quite amazing. I have a plan that I think can save many coral species from extinction, and while you are viewing some of our corals, I will give you the basic details. There are many options on how to use this technology. The corals could be grown and maintained in a permanent facility independent of the oceans, or reefs damaged by storms, construction, or global warming could be rebuilt using these corals. New reefs could also be built where there were no suitable substrates available before, such as a sandy bottom. For example, if water conditions were right, a new reef could be built in an area to attract tourism by first installing permanent stony substrates and then installing the propagated corals. My preferred plan would be the relocation of large numbers and varieties of asexually propagated juvenile corals to cooler waters. Here is my plan for saving the corals in a nutshell. Step 1 is to collect live samples of many different species of hard and soft corals and bring them back to a facility. Step 2 is using the methods I discussed in this video to reproduce these samples in a facility to create thousands of clonal corals of each species. Step 3 is to install the new clonal corals in the ocean in areas where the temperature of the water is at the low end of their survivable range. While some ocean waters are becoming too warm for corals to survive, causing them to bleach and die, other ocean waters that were previously too cold to support corals are now becoming warm enough for corals to live in. These areas might be ideal locations for relocating corals into and creating new coral reefs. In a similar way, humans also will eventually be relocating from certain areas that will be difficult to live in due to droughts, wildfires, heat waves, powerful typhoons, flooding, and sea level rise. People can move on their own, but corals can't move to better conditions, so we have to move them ourselves. With over 2,500 species of corals and hundreds or thousands of juvenile corals of each type required for success, we need extremely efficient, high-volume, low-cost methods to accomplish this. My plan is to collect as many coral species as possible, and using the high-volume techniques I have discovered, relocate them to other areas in the oceans that are more conducive to their survival. Basically, we will move their offspring to Goldilocks zones that are just barely warm enough to support them, anticipating that in the future the oceans will heat up even more than they already have. This won't be a permanent solution, but it will help the coral species survive until we can get a permanent fix to the global warming situation and start reducing the temperatures back to normal. It would be a tragedy if we fixed the global warming problem only after the corals were all gone. Choosing the new areas for relocation will be a complex decision done by experts in that field based upon ambient environmental conditions such as water temperature, depth, and makeup of the substrate, pH, water currents, natural light intensity and duration, and any other important data to help determine the best relocation area. Ideally, when wild mother colonies are collected, they will be geotagged with their location and the ambient water parameters, and that information will follow their offspring to their final destination. We may need a computer whiz for that. To be clear, this process involves asexual reproduction, where a small piece of the coral is cut off a mother colony, attached to a new rocky substrate, and grows into a new separate adult. Sexual propagation is a completely different process, occurring once a year on each reef for a week or so, where the colonies of corals simultaneously release eggs and sperm into the seawater, which combine to form planular coral larvae. These float around with the current until they settle out on a suitable substrate in a few days, if they can find one. Nearly all corals can be successfully asexually propagated or reproduced by taking a cutting from the coral and placing it in suitable conditions for attachment and growth. Much like plants can be propagated from cuttings, corals can also be reproduced this way, although corals are animals, not plants. It's a form of cloning since the offspring will be genetically identical to their parent. The biodiversity and survival of the Earth's coral reefs worldwide is now under severe threat. In 2017, Dr. Charlie Varon, known as the Godfather of Coral, and the world's foremost expert on coral reefs, said, "The Great Barrier Reef won't be here in 15 years." Unfortunately, as things stand now, I have to agree with him. I believe that unless drastic action is taken immediately, most of the coral reefs will probably be gone in our lifetime, perhaps within the next 12 years, or more likely, severely degraded to the point where they are hosting just a few hardy species of corals and other invertebrates. Biodiversity will be lost. We cannot lose these incredibly valuable resources. They are home to over 1 million diverse aquatic species, including thousands of fish species. Millions of people around the world rely on them for their primary source of protein. Coral reefs are nurseries to many of the fish species that are important to nations that rely on the fishing industry. Many islands build seawalls to protect their coastlines at great expense, but these are natural seawalls that could reduce coastal erosion due to storms and sea level rise. Coral reef replenishment programs are a good start, but current coral farming methods are highly space inefficient, very expensive, labor intensive, and most importantly, limited to stony SPS corals. It is critical that we propagate soft and LPS corals along with stony corals in order to maintain the biodiversity of our coral reefs. Soft corals are far more difficult to propagate due to their lack of a rigid stony skeleton. Previously, they were impossible to asexually propagate in large numbers. Using these methods, we can produce large numbers of juvenile corals that can then be used to create huge biodiversity reserves in the ocean, hopefully in other areas where water parameters are more conducive to their survival. Or they can be used to replenish reefs that have bleached due to elevated water temperatures or were damaged by storms, destructive fishing methods, water pollution from runoff, or due to construction. Or if you really want to think big, they could be used to create a secure coral bank similar to the Svalbard seed bank in Norway. Or maybe you have a better idea for applying this technology. If so, let me know what you think. We need to act now. I believe these techniques are the best way to preserve the biodiversity of the coral reefs. We have a special way of propagating Actinodiscus and other corallomorpharian corals that can produce nearly unlimited amounts. It will be covered in a future video. Where the attachment occurs, okay? Basically this entire system, tank, which is system 4, tank 1, is where they occur. Now you see, these are netted. I don't know if you can see, these are netted. These are unnetted next to it. All right, actually we just took the nets off, and on some of these, like yesterday, and you can see the success rate varies from pretty much close to 100%, high 90% to lower ones. Now all these have had the net removed. Now remember, there's a top net and a bottom net. We only take the top net off. We leave the bottom net off for a really long time until the coral has attached to the side. These were removed yesterday. These are the yellow Fiji leathers, and these are great. You know, that tray right there, that's the attachment on that's, you know, approaching 90%. That one's approaching 100%. 90-something, 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 100% on the paralimnelias. So you can see this system really, really works well. So we leave these in this system here from, look on the green book, but anywhere from, you know, 20 to 60 days. In addition to being a very productive propagation system, these methods are also an effective coral inventory management system. The cube size is universal for all types of corals, so they can be mixed and matched, stored or shipped any way you wish. Look, I get that it sounds crazy for one man to claim that he can save most of the coral species in the world. It sounds like clickbait. But I'm deadly serious. I think this can really work. Using these techniques, we can produce thousands, or tens of thousands, or hundreds of thousands of juvenile corals very efficiently and inexpensively, ready for implanting on the reefs. And very importantly, not just of stony SPS corals either. We can propagate all types of corals and achieve our ultimate goal of maintaining the incredibly complex biodiversity of the coral reefs. Currently, millions of dollars are being spent studying the problem of coral reefs dying, and some is being spent on reef replenishment. I think because I approached my research differently than most proposal-focused, grant-funded researchers did, that I was able to come up with these multiple methods to help save the corals of the world for posterity. If you want to participate in this endeavor, please let me know.